Eric Dauler, who is the leader of quantum information and integrated quantum physics at the Quantum Laboratory. He has a PhD in University. He currently leads efforts in developing changing electronic technologies. He's also coordinating a project developing quantum technology. And he's interested in photon and the integration of CMOS with power technology. Eric's research on single photon detectors has been recognized with the President Line Best Invention Award and the R&D 100 Award. He also was named R&D Magazine's Young Innovator of the Year. Eric's talk is Superconducting Electronics and Advanced Fabrication Technologies for AI products. Eric, thank you very much. Should get
All right, thank you, Jesus. So I'm going to go back to talking a little bit about Fab for AI, as opposed to something as profound as what Neil was telling us about. So I figured I'd start. I know many of you are aware of Lincoln Laboratory and have worked with us before, but I thought I'd say a little bit about how Lincoln Lab is a bit distinct from campus. Lincoln Laboratory is MIT's largest laboratory. It's a federally funded research and development center with its main campus out in Lexington, Massachusetts. So there's about 4,000 employees. It's spun out of MIT, or was developed for the Department of Defense in the early 1950s. So its heritage is out of MIT and out of the Rad Lab at MIT. In terms of AI generally at the laboratory, it's being advanced across all 8 of the technical divisions, but most of these efforts leverage commercially available sort of CMOS-based hardware. And so there's significant expertise in applications and algorithms that we in my group leverage, and that many of you working on other technologies might be interested in leveraging as well. But in coordinating this talk with Jesus, the interest that we're going to be talking about here is really hardware for intelligence computing efforts, or for AI. And so I'm going to talk about 3 different efforts that my group is involved with, as well as some other groups at Lincoln Laboratory. And so the first of these that I'll talk about is the Quantum Enhanced Optimization Program, which is an IARPA program, which my group is involved in, but collaboratively with MIT campus and with many other partners. So this actually has some applications to artificial intelligence. That's not the only application they're looking at, but I'll say a little bit about that. The other reason to bring this up is I wanted to talk a little bit about the model that Lincoln works in collaboratively with campus, and a model that we might be able to leverage for other efforts that many of you are working on and we heard about today. The second one, which I'll say just a little bit about, is a coupled oscillator-based computing approach. In many ways, this is sort of a classical analog to the quantum annealing approach I'll tell you about in the QEO program. There's a number of people here, Suraj, Jeff, and Sid, who can tell you more about that, and there's actually a poster later about that. And finally, I'll spend most of my talk talking about superconducting neural networks that Alexandra Evan and Alex Wynn are all working on. And Alexandra's here today if you have more questions about that. There are many larger teams in my group and across the laboratory that are helping to develop the fundamental technologies that go into all of these. They're all really early stage efforts in terms of their application to AI. So there's a number of different ways to look at new hardware for intelligence computing or for AI. And so one way is looking at the different architectures that are used. And so over here on the left are the more commonly used feed-forward architectures, where you have sort of different layers that feed forward. You can have recurrence or backpropagation. But all the way on the other end of the spectrum are these fully connected recurrent networks. And then additionally, on the device technology, there's a whole range of different device level technologies, ranging from very mature technologies like CMOS that can be leveraged with billions of transistors, to the other end of the spectrum, looking at quantum technologies. And so in my talk today, I'll sort of pick and choose a few different combinations of architectures and device level technologies. And the first of those that I'll talk about is a quantum technology that's basically using locally connected recurrence. So to set the stage a little bit, as you heard this morning, there's one way to do very efficient computation is to think about the physics of the devices that you're using and to try to leverage that physics to do the types of computation that you want to do. And so in particular, what you could imagine is that you could create an energy landscape that represents the problem that you're trying to solve. And you could do this by coupling together different harmonic oscillators. And these could either be classical harmonic oscillators or quantum mechanical oscillators. And by doing this, you create some Hamiltonian, an Ising Hamiltonian, that's either a quantum mechanical or a classical Hamiltonian. And this represents an energy landscape, and the minima in that landscape represent optimal or near optimal solutions. And you can use this type of mapping to solve a lot of NP-complete, very hard for classical computing types of problems. So as a result of this, these network of coupled oscillators can be used to solve problems that are very difficult to solve, in quotes, efficiently using modern digital computers. And one reason that I put solve in quotes is that oftentimes you're not trying to come up with a single correct answer. There are many different answers that you might want to, that might be tolerable answers that are near optimal. And additionally, it may be that you don't even set up this problem or this computer to necessarily solve the problem that you're trying to solve, but instead you're trying to represent the high dimensional probability distributions that represent your problem, and it's really by that you're coming up with these machine learning techniques. And so what I mean by this is that you may not use this computer where you have these coupled harmonic oscillators to solve every problem you're trying to solve. You may use it in order to come up with a machine learning algorithm that you can then apply to classical hardware. And so first I'll talk about the quantum mechanical version of this, and then I'll come back to a classical version of this. So in terms of the quantum mechanical version, there's actually been an enormous amount of work done. And so much of this work was pioneering work by the company D-Wave, a Canadian-based company that is building quantum annealers. And so if you look at their website, machine learning is one of the key applications that they highlight on their website. They've chosen a particular approach to building these quantum annealers, which has allowed them to get to a relatively large number of qubits and to start looking at optimization problems and the potential scaling. But it doesn't capture all the physics that might be possible with devices. And so the IARPA QEO program, Quantum Enhanced Optimization Program, is really looking at a different set of trade-offs in designing the hardware. So in particular, looking at much higher connectivity. I'll say a little bit more about the connectivity of the D-Wave system in a minute. But with much higher connectivity, you can imagine embedding problems much more efficiently. The QEO program is also looking at much higher qubit coherence. So one of the limitations in the D-Wave system is that their qubits are not particularly coherent, and this has limited their ability to look at how quantum enhancement can really play a role in quantum annealing. And finally, there's better control flexibility by more directly controlling each of the interactions between the qubits. So this is an image of one of the packages that we built for the QEO program. And I want to say a little bit, as I said, about how we're a part of this program and one of the models that you might imagine using to build larger scale demonstrations of any AI hardware. So our role in the program is a few different things. So one is that we host these research test beds. So these are very large physical infrastructure. There's going to be thousands of channels of digital to analog converters that control each of the qubits and each of the couplers in the system. They're dilution refrigerators, so relatively expensive and hard to maintain infrastructure for controlling all these systems. Additionally, we act as sort of like a foundry where we fabricate these 3D integrated chips that provide for very high coherence of the qubit and also allow routing in many different layers in order to get high connectivity between all those qubits. And so this fabrication process is run in a fabrication facility at Lincoln that is an ISO certified fabrication facility. It runs 24 hours a day, has a team of many tens of technicians and engineers that are helping to maintain all the tools. And then like a commercial foundry, we have design guides, we have design tools that allow you to simulate what you're going to get out of building into this fabrication process. And then finally, we work with the performer team, which includes a lot of industry participants, universities from around the world, including MIT, and they design into this process. The process then puts packaged devices into these test beds, and then they run the test beds in order to study what they need to about how these quantum annealing systems work. And so you can imagine that this might be a similar model that could be adopted for other AI technologies. And so if we abstract this a little bit, the pieces that I've shown here are really that there need to be hardware demonstrations at a scale that's useful for really building up a capability and bringing it to a point where commercial markets can take over. There need to be what I'm calling technology platforms, things like CMOS, where you can design into a fabrication facility that gives you the yield but still the flexibility that you need. And finally, there's some foundational science and engineering that needs to inform what it is that you want to build, what these platforms should look like, helps advance new components into those platforms, and then decides what research questions need to be answered by these demos and does all the design work. And so advancing these hardware demonstrations are really going to require cycling around this research cycle in a way that supports both the necessary flexibility and maturity. So something like advanced node CMOS certainly provides the necessary maturity. You can get the yield you need for very large scale demos, but it has limited flexibility. Most commercial foundries are not going to allow you to tweak the CMOS processes that they're run. And so one of the roles that Lincoln might play is that we can provide expertise and ideas in a subset of the relevant scientific and engineering disciplines. We help to design a lot of those coupler trees that are being used by the QEO program, in addition to helping to maintain some of these more infrastructural capabilities. And we can provide the fabrication capabilities that combine both stability and flexibility. And finally, we can provide engineering support for their larger scale demos. So then, using a model like that, you might imagine that there's a couple different areas that Lincoln has fabrication or device level technologies that could be leveraged. So one is in photonics. And so I'll point out very quickly an idea that a team at Lincoln is working on that's looking at fully connected recurrence that's enabled by using photonics. And so this, similarly to the D-Wave system and to the IARPA QEO program that I just told you about, is a way to create these Ising Hamiltonians. But rather than doing it with quantum mechanics, it would be you're looking at classical harmonic oscillators. And so if you look at the architecture that's adopted by D-Wave, it's this chimera graph where there's only a very few number of qubits that are connected to one another locally, and then this unit cell is repeated in a way that has lower and lower connectivity as you go out. The coupler trees that we're using for the QEO program enable much higher connectivity, but it's still unit cells that have tens of qubits. It's not connecting tens of thousands or hundreds of thousands of elements in a fully connected way. And so in order to scale up to having these fully connected graphs where at the 100,000 level you'd be talking about billions of connections, an idea that we have is to use photonics, to use pairs of VCSELs, vertical cavities, surface emitting lasers, and photodiodes that can allow optics through free space to enable these very high connectivities. And so if you're interested in hearing more about this, there will be a poster this afternoon about it. So I encourage you to talk with Jeff, Suraj, and Sid about more about their work. Then the last section, which I'm going to focus most of my time on, is looking at more commonly used architectures, things like feed-forward or backpropagation, coupled with classical superconducting electronics. So first, to set the stage a little bit, I'm going to give you some background on superconducting electronics. So two reasons that it could be very attractive for next generation beyond CMOS computing is that it has very low energy. So you can see here, this is a graph that's showing the bit flip energy as a function of delay. And so there are technologies, superconducting technologies that are approaching the Landauer limit. And in fact, there are ways that you might evolve these to do reversible computing and even go beyond the Landauer limit. But these are very energy efficient technologies. The other thing is that, as we heard about today, data movement to memory or otherwise is one of the main limitations of conventional approaches. And superconducting electronics eliminates the losses associated with this in terms of resistive losses. Because they're superconducting, there is no resistive loss. So very narrow, very short pulses, picosecond class pulses can be transmitted with essentially no loss over long distances. So it's a solution to the high energy overhead of data movement in conventional processes. The other reason that I would say it's attractive is that it's actually a relatively far progressed technology. So we at Lincoln fabricate thousands of wafers per year in this fabrication facility that I mentioned that runs 24 hours a day. They're highly planarized processes with many metal layers, so you can do the routing and other things that are of interest. You can build relatively large-scale circuits, so this is about 1 million Joseon junction circuit that we yielded. And this is about a 100x increase over the last 4 or 5 years that have enabled this. So the technology is progressing well, and you can get to relatively large-scale demonstrations at this point. But there's been fairly little work done on using it for AI specifically. The focus of the efforts have been really to emulate classical CPUs and classical technologies. So in looking out to neuromorphic hardware, there's a couple of different parts of the trade space that you might imagine. So a lot of the CMOS approaches use digital solutions, digital designs. The superconducting technologies are really much more amenable to analog approaches. There are also NIST and other groups have been looking at emulating neurons in terms of having spiking behavior, and the SFQ pulses, these superconducting pulses that get transmitted, make that a natural idea to have. But in fact, we're looking at a different approach that uses an adiabatic cell to be much more energy efficient, and we believe just as fast and sort of better matched to the superconducting electronics. And so if you compare the energy and the time that it takes to do a multiply accumulate or do a classify, you can see that these superconducting technologies actually have, even including the overhead of doing cooling, have very attractive energy numbers, in particular this approach that I'll be telling you about today. And they can also work at very high speeds, so few nanosecond scale classify times. So going back to the way that it's done with digital electronics, with CMOS, what we're looking at here is if you want to emulate a neuron where you have weighting of a bunch of inputs and then a nonlinear function that's applied to the sum of those inputs. This is done in digital electronics using multipliers that are made up of adders and that involve many transistors in order to do this. And so what the sort of key idea is for doing this in superconducting electronics is to move into the analog domain and to instead use a network of inductors where the analog values of these inductors are what set the splitting, what allow you to do the weighting or the multiplication. And so these are very compact cells. This is 10 cells that are sort of microns on a side, 10 microns or so on a side. And in contrast to other device level technologies where it's the fabrication of the feature that is what defines the accuracy, here you actually set the weighting, you set the inductance digitally. And so this small cell, it's a small circuit. The same kinds of circuits that are used in the D-Wave system are what allows you to create a tunable inductor. And so you can set this inductance value with very high precision. In fact, the fact that you use superconductors actually allows for a particular kind of quantization or digitization that's tied to fundamental constants. And so these can be very accurate and sort of aren't subject to the same sort of fabrication defects that other technologies are. So using this approach, the multipliers become very small. They become sort of tens of microns on a side. We then can sum all the currents and apply a nonlinear function. And so all these pieces become much smaller than they were in the CMOS case. And we can combine digital and analog functionality in a way that's sort of ideally suited to the function that it's serving. And to demonstrate that this is a feasible approach, the team so far has been looking at simulating circuits. So looking at this small neural network here, they've actually done simulations of all the superconducting electronics and mapped it to an electrical simulation. So we're now at the stage of having designed some circuits into our fabrication process, and we'll soon be testing those to see how they work. But some of the results from the simulations are shown here. It can in fact classify, based on the simulation, it can classify these different images that were in the training set. And in fact, the speed of this is very fast. You can see this is only a few nanosecond scale. It can run at gigahertz type speed, so it can do very rapid classification of images. There are, however, a lot of remaining challenges. So certainly, as I said, we're just getting started on the device or the hardware demonstrations, and so there will be a lot of work to get to larger scale prototypes. We'd like to work with others in terms of jointly identifying applications, developing more automated design tools, and exploring techniques for validating and debugging larger circuits. There's also a lot of work needed for network training. We have some ideas for how to do back propagation and how to do training, but there's still a lot more work to do there. And finally, at the device level, the I/O from these circuits is still a big challenge, and so we're looking for collaborators who have ideas for new I/O devices, packaging with many parallel connections. We have some work in 3D integration, but there's certainly other ideas that we'd like to explore. More direct integration with data generating devices is similar to what Max Strulacher was talking about this morning in terms of directly integrating sensors. And finally, data compression and reduction techniques. So in summary, the lab is really actively pursuing and interested in further collaborations with campus and with others to develop new approaches to intelligent computing hardware. We have a few technology platforms ranging from customized CMOS to photonics to superconducting electronics and quantum circuits that we're happy to work with campus to leverage. And then there are many challenges that will benefit from more cross-disciplinary interactions. So we're looking forward to working with many of you that would have ideas for bringing forth or advancing some of the technologies that we're working on. Thank you.
Yeah.
Where are you on the simulation version of classical supremacy? There's been a lot of historical debate about quantum simulation versus best practice classical optimization.
You're talking about for quantum supremacy?
But quantum supremacy not for fully entangled states, but just the question of historically comparisons of quantum simulation have been against ancient ideas in classical simulation versus best practice in classical, like heuristics for TSP.
That's right.
And so where are you relative to best current practice for best classical solution for heuristics for hard simulation optimization problems?
So there are no, the QEO program is still early in its phase, but even outside of the QEO program, there are not quantum processors that can beat known classical algorithms. So what QEO is doing is it's set up a method by which we're going to try to improve the way that we're comparing to classical approaches. So there's a team at NASA and at Texas A&M University that are working on trying to better define problems that really do state-of-the-art classical approaches and compare them to quantum approaches. There's certainly domains, so the QEO program is looking at domains that D-Wave isn't, like non-stochastic environments. There's a better chance that there'll be a quantum advantage, but I would say there is no known quantum advantage for quantum annealers yet.
Again. Thanks. I'm curious about the materials that you are using. I am assuming that you are using some low temperature superconductors, niobium base or something, and I'm curious about which temperatures are you supposed to operate these kind of devices, and also what is the perspective towards like high temperature superconductors, for instance. Is possible to keep the quantum coherence at the device level or something?
Right. So for the quantum technologies, the QEO program that I mentioned first, those are at tens of millikelvin temperatures.
Okay.
The later neuromorphic technologies based on classical superconducting electronics is at 4 Kelvin. So they are in fact niobium circuits. There has not been a lot of progress towards making complex integrated circuits with high temperature superconductors. That's certainly an area that could be of interest. So the cooling penalty for going to 4 Kelvin for relatively large scale systems on the order of a few hundred to 1,000x. So if you could move to a higher temperature superconductor, you'd get 10x very easily. improvement in energy efficiency. So that's certainly of interest, but I'm not aware of a lot of progress in that direction.
Thank you.
So one thing with all these different platforms, I was just curious, since people on the outside know about them, do you see any of these being driven by reasonable commercial applications, or is it kind of like, from a commercial point of view, we're still trying to find what the applications would be?
Are you talking specifically about quantum systems or in general?
I'm actually in general for any of these platforms that you're doing, because I know Lincoln, of course, is looking at particular applications in general that let's say aren't commercial, right? But do you see any demand from the outside for commercial activity?
So I think the photonics, so as you look along that device axis, there's definitely commercial drivers for. I think moving more towards the superconducting electronics and quantum, they're in the research domain right now. I would say there aren't any products that are beyond further advancing the research at this point.
Yeah, I didn't mean what stage they're at, but if there's hope of an application. So you could be 15 years out, but there's a really important application, right?
Right.
Commercially, right? So I was just curious. So photonics, what are the applications that people are interested in?
So it's, for I/O for existing electronics is certainly one. For communication systems, there's a lot of photonics. You branch out in terms of the wavelengths that are used. There's bio applications for photonic circuits. So I think there's going to be a talk on a neuromorphic approach using photonics. So I think there are certainly drivers for photonics. I think more to the right, they're more exploratory, and it's less clear at this point. I would say that it's less clear what the advantage is going to be, but they're research fields.
More questions? A question on the how you prepare the weights. You said that you digitally set the value of the inductance.
That's right.
So how is that the flux quantum, the number of flux quanta that you trap in this circuit? Is that how it works?
Yeah. So it's essentially like a flux stack, so a flux digital to analog converter, and so you can input what inductance you want, and it is based on the number of flux quanta that you load into this circuit.
So is that more suitable for learning than inference, or the other way around?
It's so. I guess ask the question again.
Well, there's learning and then there's inference in terms of the use of these neural networks. Is there, I can get a sense of what side is this technology more suitable for?
Okay, so the way we've designed it so far, it's just forward propagation. So we haven't done a lot of learning. We haven't done the back propagation. We certainly have ideas for how to do that, but right now, that cell is really just meant to help set the weight.
All right, if there are no more questions, we move on with the program. Eric, thank you very much.